Okay, so we're going to take a look now at 6.3, which we finally get to do multiplication and division. And the multiplication and division is usually what causes problems with the addition and subtraction or the comparing of things, right? So now we actually get to all of the problem-causing things. But they're the ones that students usually have a little bit easier time with, so at least that part of it's good. All right, so let's first talk about what multiplication looks like. And to do multiplication is a lot easier than to do addition, at least in regard to fractions. So when you're multiplying fractions, you don't need to worry about common denominators. In fact, if you start getting common denominators, you're going to get really big numbers everywhere, and it's not going to be helpful at all. So with multiplication, all you need to do then is to multiply straight across the top and multiply straight across the bottom, right? Okay. What I'd like to do is I'd like to show you a diagram that represents how this could be drawn. Okay, so I've got the number 3/5 times 3/4. And what I'm going to do is, it says a rectangular region. I'm going to draw a large rectangle, and I'd like for you to do so as well. Vertically, we are going to split our rectangle into, well, 5, I guess. 5 regions, because it says 3 out of 5. Okay? So do your best to make your regions look reasonably the same size. Mine are probably not going to. Hey, you know what? It's not so bad. So we have 5, should be roughly equal regions. Okay? If you were told that you were supposed to shade in 3/5 of this, you would have drawn the 5 regions, and then you would shade in 3 of them. So that's what we're going to do next. We're going to shade in 3 of our regions. I don't care which 3 you shade in. Just in the sense of what we're about to do, it probably is helpful if you put them all beside each other. Not like every other one like the flag. Okay, just thinking. All right, next thing you're going to do is you're going to split it into fourths, because it says 3/4 as my next fraction. And the fact that it says 3/4 is just, that's what it says. It's not important that it's 3. It's not important that the 3's are both on top here, I guess, okay, is my point. So here's how you do that. Before we split things vertically, now we're going to split them horizontally. So to split things into fourths, the easiest thing to do is split them in half twice. Okay, so I've got a grid. Now I want you to sort of ignore the red and ignore those vertical lines. I have 4 horizontal stripes. How many am I supposed to shade in? 3. Okay, so choose yourself I'm going to choose a different color just to avoid the issues. The other thing you could do is you could change your direction of your shading so that the crisscross is clear, instead of it just looking like you've just shaded the same thing in the same direction again. It almost even looks patriotic, doesn't it? Okay, then the solution from this diagram of 3/5 times 3/4 is actually the double shading. How many boxes got double shaded? 9. Out of how many boxes total in my picture? 20. And you can see exactly that that works with our definition of how this multiplication is supposed to work. You multiply across the top, 3 times 3 is 9. Across the bottom, 4 times 5 is 20. So this is a diagram that represents this concept. Does that make sense? Okay. So I'm going to take a look then at some of the properties of multiplication. Multiplication has an identity and an inverse property, just like addition did. The identity property is, an identity is an element that when you multiply it by something, it doesn't change the value. And the identity element is the number 1, right? If you multiply 1 by anything, anything doesn't change. 1 times, my head is my head, or 1 head. All right, so we have 1 times A over B is A over B, and it doesn't matter if the 1 is in the front, it doesn't matter if the 1 is in the back, that's a commutative property that's going on there. It's still equal to A over B. Now, an inverse is actually the number that you multiply it by to get it back to the number 1, so to turn it back into the identity. So if you have A over B, you'd multiply it by B over A. And that's called, what is it called when we do this sort of a flipping? Do you remember what the real term is? It's a reciprocal. So the reciprocal is basically the flip of a fraction. So if you flip a fraction upside down, you've taken its reciprocal. All right? You don't introduce a negative or anything like that. That's another concept that comes into algebra later on with other things. It's just flipping the fraction upside down. That creates the inverse. So if you have, let me do one here just real quick. So if you have the number 4 19ths, the inverse is what? 19 over 4. No problem, right? Okay. Now, we need that property along with some of the others as we're solving equations and we're working other pieces later. But we need a couple more. So one we need is the distributive property of multiplication over addition. So if you have a number in front here, so the a over b, c over d, e over f, they're rational numbers. Okay, so they've got integers on top, integers on bottom. If you have a over b times this quantity, you can distribute the quantity a over b across those parentheses. So it looks like this. So it becomes a over b times the first fraction c over d, and then a over b times the second fraction e over f. And then that's helpful sometimes, especially if you're dealing with pieces inside that will simplify easier if they're multiplied first. The second one, multiplication property of equality, is definitely something that we use when we're doing simplification of equations. So if I have two fractions, a over b and c over d, they're equal to each other to begin with. That if I multiply both sides by another fraction or whole number or whatever, they're still going to be equal, right? So if I introduce this e over f and I multiply it on both sides, the equality stays the same. It still stays equal. And the idea works with inequality as well. So if I have an inequality where the first fraction is bigger and I multiply by an e over f, okay, so everything in the first piece up to here is the same except what? What's different from line 1 to line 2 before my blue little... Yeah. This first one says that e over f is greater than 0, which means it's a what kind of number? Positive. And the second one says e over f is less than 0, which means it's a negative. So remember with inequalities that if you have an inequality, in this case we used a greater than, but it doesn't really matter, a greater than inequality, and you multiply both sides by a positive number, then it stays a greater than inequality. Okay? In other words, if I say 2 equals, let's do it right. 2 is less than 5. And I multiply both of them by 3. Well, 6 is still less than 15. Okay? Nothing changed. Okay? However, things do change if they're negative. So if I still started out with my 2 is less than 5, and instead of multiplying by 3, I multiply by a negative 3. I end up getting negative 6 on the left and negative 15 on the right. And we've talked about this actually earlier today, right? A bigger negative number is actually a smaller number. So the direction of my inequality changes. And that changes anytime you're working with a negative multiplication inside of an inequality. So one of those ones that we have to remember is that we switch the sign. So when we multiply by a negative, we switch the direction sign. The last one's a great property. It simply says what? Anything times 0 is 0, and this is the 0 property of multiplication. That's all it is. Okay, anything times 0 is 0. All right, so what we're going to do is we're going to take an equation and we're going to solve it. Okay? But the difference in what you've done before with this is that you're going to write down every single time you use a property. Okay? There's going to be a lot of properties. You don't realize how much of this stuff you're using as you're using it. So, excuse me, if I'm taking a look, actually I think it's the next one that has a lot of properties. This one just has a few. Yeah, it is. All right, so taking a look at this right here, 3/4 x equals 1 over 5. And my goal is to solve for x. What should I do? Multiply what?
The inverse.
Okay, so what is the inverse going to be?
4/3.
Okay, so Heather would like to multiply by 4/3. And she wants to do that, and in doing so, she's using the multiplicative inverse property, because that's the multiplicative inverse. In other words, that's why she chose the 4/3. She's using another property as well. Number 2, right? She's using the multiplication property of equality. That's what allows me to multiply both sides and still put an equals between them once I do that. So this is the multiplicative inverse property, and this is the What do they call it? Multiplicative property of equality, multiplication. Multiplication property of equality. Okay, so let's do that. That gives me x on the left. What do I get on the right? Oh, well, let me do it. Go ahead. This actually gives me 1x on the left. Why does it give me 1x on the left? 3/4 times 4/3 is 1. Right, that's part of that multiplicative identity property, or multiplicative inverse property that became 1. What do I get on the right? What is 1/5 times 4/3? 4/15. There's not a property in that per se, but there is one more step. Right now this says 1x equals 4/15, which is never how we write this. How do you usually write it? X equals 4/15. Now why in the world do we not have to put that 1 there? It is understood, but there's more to it than that. It's the identity property, right? The multiplicative identity property is what allows us to say that 1 times x is x. Right? Yeah. So this is the multiplicative identity property. Okay, so that was just a one-step one. The next one isn't. The next one has same directions, but it says 2x over 3 plus 1 over 4 equals x over 6 minus 1 over 2. And there's a lot of ways you could start. So somebody suggest me an idea of how to start. You can only cross multiply if it's one fraction on each side. Right? We've got 2 fractions on each side. So what we could do, if you really like the cross multiplication idea, is we could turn each of the fractions on each of the sides into a single fraction. That's a possibility. So you would have to actually combine that 2x over 3 plus 1/4, and you'd actually have to combine the x over 6 minus 1/2. Do you want to do that, Lexi?
Well, that's what I was thinking.
Okay, we can do that. Does anybody else have a better suggestion or something else you'd like to try instead? It doesn't matter.
You could subtract the x over 6.
Like to combine it with the 2x over 3. So we could do that as well. We could get all the x's on one side and all the other numbers on this one side before we do the combining. At some point we're going to combine, so it doesn't really matter. But, okay, so what do we want to do? Somebody tell me which one you want to do. We've got 2 options here. All the x's on one side? Okay, is that all right with you, Lexi? Okay, so what Brendan wants to suggest is that we move the x over 6 to the left, so we would subtract x over 6, and that we would subtract the 1/4 to the right. Okay, so I'm doing this sort of like it's an addition problem, okay? So I now have 2x over 3 minus x over 6 equals negative 1/2 minus 1/4. So let's pause there for a moment and decide what allowed us to do that. What allowed us to do that addition and subtraction of those quantities? Yeah, and we called it the additive property of equality when we did it before. So this was the additive, kind of like the multiplicative property, but we did it with addition here. So this is the additive property of equality. There was another property, though, that we used in there, too. That property was the additive identity and additive inverse. And I'm sort of writing them all together because we did them all together. So the very fact that we did something to both sides is the property of equality. The values we chose them because they were additive inverses. That is, I chose to put minus 1/4 on both sides because 1/4 minus 1/4 is 0. I mean, that's why we chose it, right? We chose that value on purpose because it was the inverse, the additive inverse, and because the additive inverse becomes 0, and then I don't have to write it down. Okay? You're looking confused, Heather. Are you okay? Yeah. Okay. Any questions? Okay. Now I still need to combine these, so I need to get common denominators. Okay, so let's do each side separately. If I do the first side, what would the common denominator of 3 and 6 be? 6. So what am I going to do to the first fraction? Multiply it by 2. So I end up getting 4x over 6 minus x over 6. What would the common denominator be on the right-hand side? 4. So I'd multiply the first fraction by 2 again. So I would get 2 over 4. Sorry, negative 2 over 4 minus 1/4. And what I'm using is I'm using the idea of equivalent fractions. I mean, whoops. Right, I've kept those fractions equivalent by multiplying the numerator and the denominator. Minus x over 6. 3x over 6. What's negative 2/4 minus 1/4? Negative 3/4. So we could simplify the left-hand side, or we could cross-multiply. I've put Lexi off long enough on the cross-multiplying, so that's what we're going to do next, okay? So we're going to multiply 3x times 4 to get 12x. And then we're going to multiply 6 times negative 3 to get negative 18. And then what? Okay. So what I actually did here is I used is a property of fractions too. So I think do we have a name for it? Let me take a look. I'm looking back in section 6.1. It may just be a property of equivalent fractions. It may have been written that way. Yeah, it's theorem 6.2 is what it actually is. So if you just write equivalent fractions, that's okay. Just like the last one is fine. Okay, now what? Divide by 12. What allows me to divide by 12?
Is that the identity property?
It's not the identity property. Well, the inverse property and the identity property come into play in it, so I'll write those down, but there's another property that I'm looking for. So this is multiplicative, identity, and inverse. That is how we chose the 12. And the fact that 12 divided by 12 is 1, and 1 times x is x. But what else allows me to do that? Nope, didn't distribute on this one.
Have we gone over it yet?
Yeah. It's the multiplication property of equality. That is, why am I allowed to even divide both sides by anything at all? Because I have a property that says I can multiply both sides by the same value. Division by 12 is the same as multiplying by 1/12, right? So if I'm allowed to divide both sides by 12, it's because I'm allowed to multiply both sides by 1/12, and I'm allowed to do that because of the multiplication property of equality. This needs to be reduced, and we have a final answer. What does x equal? It's negative something. Negative 3/2. Sorry, I'm out of space beneath there, but negative 3/2. If we reduce, they're both reduced by 6. Okay, so multiplication, we also have division. A over b and c or d are rational numbers, and if we start talking about division, a over b divided by c over d equals e over f. If and only if e over f is a unique rational number such that c over d times e over f is equal to a over b. And I want to use, again, whole numbers to show you this works, not because fractions don't, but just because you get the same idea either way. So if you have I said numbers. How about, we'll do 6. If I do 6 divided by 2, I know it equals 3, right? The reason I know that is because 2 times 3 equals 6. And in fact, that's usually how we first start talking about the idea of multiplication and about division, is we refer back to multiplication. Okay? So we say 6 divided by 2. Well, how do I get the answer? Well, what times 2 is 6? Oh, it's 3. This missing parts idea. But then there's an algorithm for division of fractions. So some of you probably remember this algorithm. It says that if I have a over b, and I want to divide by c over d, what I can do is I can simply flip c over d over, take its reciprocal, and I can change my division into multiplication. Do you guys remember that? So what I want to actually show you is why in the world does that work? Because that seems like a really nice sort of a rule, and again, you're not going to show this to your students, but you should have some kind of an idea of how it works. Because at some point, if you're teaching this, some very bright kid, or smart aleck, I'm not sure, will ask you why, and you should have an answer beyond, I'll get it back to you on that, which you probably will say I'll get back to you on that, but you should know where to look and how to get back to him on that. So I want to show you why this actually works. So we're going to take that A over B and divide by C over D. But what I want to do in doing that is I want to write it differently. I want to write A over B like this and divide by C over D like that. Okay? I know, fractions instead of fractions, no fun. But I just want to write it that way for a moment for you to think about something. Somewhere along the way, you have this idea that I can't have a fraction divided by a fraction as a final answer. And that's true. We don't ever leave anything like that as an expression. So what do? Well, how can I make this C over D go away? Right. I can actually multiply this by D over C. And why in the world would I want to multiply C over D times D over C? Because I get 1. But this is fractions we're talking about. That is, I've got a big overall fraction, and I have used the big overall fraction, and I have multiplied the denominator by D over C. So by equivalent fractions, I also need to multiply my numerator by D over C. Okay, we multiply the top and the bottom by a same fraction. We did that because the denominator now is 1, and the numerator is A over B times D over C. And we wanted the 1 in the denominator because what happens when you divide by 1? Yeah, I mean, in essence, nothing, right? Nothing happens. It stays the same. You get whatever is on top. And notice what is now on top. It's exactly what you remember doing. A over B times D over C instead. That's why that's working for you. It's all about the reciprocal idea and simplifying. I want to show you one other thing about multiplication, or in this case division, that's very helpful. Students really have a big problem, and some of you probably do too, with what in the world you would need to divide by a fraction for. So if I'm looking at how do I divide 6 divided by 1/2, I mean, we can do this, right? I mean, we can do, oh, that's 6 times 2 over 1, that's 12. Okay, great. I mean, like I can do that computationally, but if I ask you to create a problem where you do that, that becomes a little trickier. So I want to show you a diagram on how to think about this in a little bit more easy, fluid kind of way, maybe. One way to think about 6 divided by 2 is to think about having 6 objects. They should all be the same. So pretend all my circles look alike. So you have 6 cookies, or whatever, 6 objects, something that you can cut or can you split apart. So if I have 6 cookies, one thing that this 6 divided by 2 means right here is I have 6 and want to divide them into 2 groups, right? That's one way to think about 6 divided by 2. We did that last semester in Math 1, for those of you who did that. The other way to think about it is I have 6 objects and I want to put them in groups of size 2. Do you see the difference? The answer's 3 either way, but the picture is different. If I have 6 objects and I want to put them into 2 groups, it looks like this. I just split them into 2 different groups. If I want to, I can take 6 objects and put them in groups of 2, like that. And the question is, how many groups do I have instead of how many are in each group? This kind of a description is actually far more helpful when we're looking at the idea of dividing by a fraction. So this idea would be the idea of saying I have 6 objects. Again, you can call your objects whatever you'd like. And I want to make groups or, collections or something, groups of size 2. 6 divided by 2. Now let's do 6 divided by 1/2 and have that same idea. I have 6 objects. They're looking less and less like each other as the farther I draw. Pretend. I have 6 objects. They're supposed to be all the same size. And I want to put them in groups of size, what? 1/2. So using tennis balls as this example would not be a good plan. Cut the tennis ball in half, it's useless. Cookies would work just fine, especially the big cookies, right? Okay, so I can actually take this idea and I can make them into sizes of 1/2. Now I know that sort of looks like I divided each of them by 2, and in essence I did, but not from that perspective. I did not divide by 2. I divided by 1/2. I divided by 1/2 by making each of them size 1/2. So now I have 6 objects of size 1/2. Okay. So what could you do this with? Well, if you had the 6 divided by 1/2, you could say something like that. I have 6 cookies. Okay? And if I have each of my cookies as half of a cookie, that is half divided by 1/2, how many people get a cookie? You get 12, right? There's 12 halves here. So that works pretty well. Okay. At this point right here, we're getting into discussion of exponents. So I'm going to pause and we'll pick this up next time.